All right, today's lesson is on binomial probability. So our objective is to find binomial probabilities and analyze binomial distributions. It's not quite as bad as it sounds if you have your handy-dandy graphing calculator. All right, so there's this lovely little box that explains what we're doing, kind of, but I think it'll make more sense when we get some numbers in there. So it says finding a binomial probability. Binomial experiment with n trials. The probability of k successes is probability of k, so that's just showing you the notation. And then they're using the combination symbol. So we want to use that button on our calculator. N trials with k successes. And then they have p to the k power, 1 minus p to the n minus k. Probability of success on each trial is p. That's really confusing. So we're going to go through some examples and hopefully get this down. And there's not a lot of room at the bottom of this box, so I'm going to probably use the margin a little bit too. So it says calculate the probability of tossing a coin 15 times and getting 3 heads. All right, so what we're going to do is we're going to set up the first part, the NCK part. So we're tossing the coin 15 times. So that's the first number we need to write down. Then we're going to have the C for combinations of 3. So we're finding combinations of 3 out of 15. And then we have to think about what the probability is of getting heads each time we throw it. So a coin has heads and tails. So your probability of getting heads is 1/2. And we're going to get 3 of those. So that's where the third power comes from. And then we're going to do this thing where we take 1 minus the probability, which is 1/2. So all the p's in this formula are the probabilities. Like for this case, it's 1 out of 2. And then the power up here is going to be 15 minus 3. And we'll change that in a second. So we're going to use the calculators to do most of the hard work here. So I have 15c3, 1/2 to the third power. And then we're going to go ahead and do 1 minus 1/2. A 1 minus 1/2 is 1/2. We're going to go ahead and do the 15 minus 3 and get 12. And then we're going to type all of this into our calculator. So I'm going to zoom out a little bit so I can get the calculator right up next to where we're working. And we'll type it in. So if you're using the newer TI-84s, you can go right into your math menu. So there's the math button down here. And then we right arrow over to probability. And we want number 3, the NCR. And we'll put in our numbers 15 and 3. And then if you hit your right arrow key, you'll come back out of that little subscript and we'll write times. And I'm going to go ahead and just put in the fraction because we'll have some different fractions as we go. So I went ahead and put 1/2 in parentheses, then hit my power key to the third, then you right arrow, parentheses, 1/2, and then to the 12th. So thankfully for us, the calculator will do a lot of this for us. And it's going to give us a decimal. So 0.013885. We're going to go ahead and just round this decimal off. I think I'm going to keep 3 decimal places. So where that 3 is, it'll round up to a 4 since the next number is an 8. So what I'm actually going to write on the paper is 0.014 is my probability. So just a little bit more than 1%. So if you were tossing the coin 15 times and you're getting exactly 3 heads and all of the others are tails, your probability would be about 1%. So not very likely. So this is the formula that we're going to use on all of these. So let's go ahead and look at the next box. It says calculate the probability of randomly guessing all of the correct answers on a 25 multiple choice test which has 5 choices for each problem. This is kind of interesting because I know we've all guessed on multiple choice tests. This would be like you know nothing about the test, you're just sitting down and picking completely random answers. So, and you're wanting to get all of them right, which is not going to be very likely. So there's 25 questions, and we want to get all 25 of them right. So we're going to do 25C25. Your chance of getting, the probability of getting a question right, if there's 5 choices, is 1/5. And we're going to take that to the 25th power. And then you do 1 minus 1/5 in here. And you'll have 25 minus 25 up here. So we'll clean that up here in a second before we type it in. So it's 25, C25, 1/5 to the 25th. And then 1 minus 1/5, we could go through lots of thinking about that, is just 4/5. This is the complement to the probability. If there's a 1/5 chance you'll get it right, there's a 4/5 chance you're going to get it wrong. And then that's going to be to the 0 power because we're trying to get all of these. And that actually turns that part into 1. But we'll go ahead and type the whole thing in just to illustrate that the calculator can do it. So if you hit your math key, arrow over to probability, we're going to pick number 3. We'll do 25 and 25. Hit the right arrow to come out of that. 1/5, close parentheses, to the 25th power. You can do your right arrow. And then this part is the part, if it's 0 power, technically this goes away. But sometimes when we're working, we just don't think about that, and so we'll just type the whole thing in as is. And it's giving us some scientific notation, which means this number times 10th to the negative 18th. That is a very, very, very small number. We're going to go ahead and just use scientific notation on that. So I'm going to round it off and say it's about 3.36 times 10 to the negative 18th. If you wanted to get creative, you could put 0.0000000000000000336, and you could write that all out. But this is why they invented scientific notation, so we don't have to. Okay, let's do the bottom problem. Calculate the probability of randomly guessing 20 correct answers on a 25-question multiple choice test, which has 5 choices for each problem. So now we're kind of lowering our expectations a little bit. We're only going to try to get 20 of them right, which is an 80. We're just going for a B. So it only changes slightly. We'll have 25, C 20. And then we have 1/5 chance of getting each question right. We want to get 20 of those right. And then since we already did this subtraction up here, I'm going to go ahead and change this to 4/5, but it's 1 minus 1/5. And so there's 4/5 the chance for those of getting them wrong. And we're going to say, okay, we're going to miss 5. So that's where the 5 comes from. There's 5 of those we think we're going to miss. And then we'll go ahead and put that into the calculator. And so to show you something cool so we don't have to type all this in, on these newer calculators, you can arrow up and highlight it and then just hit enter, and it'll copy all of your work down for you. And we can just go in and change all the numbers. So this power up here is a 5. This becomes 20. And this becomes 20. So that way we didn't have to type it all in again. You certainly can type it all in again. But if you're doing the same basic problem with just little changes each time, that's just a nice way. You can just enter that original thing and it'll type it and you can change it. So it's a little bit better. We only have 9 zeros before we get to an actual number. So we'll go ahead and write that one in scientific notation as well. So it came out about 1.83 times 10 to the negative 10th. It's still not very likely if you're truly guessing on every question on a multiple choice test that you'll get 20 out of 25, which would be a B. It's just not a very good chance. This is getting exactly 20 out of 25, so that's the chance for that. All right, so what we're going to do now is look at building a binomial distribution. And actually, the next 3 boxes go together. I spread it out. So it says, in a class of students, the probability of a child eating the school lunch is 0.28, so that'd be 28%. If you just pick somebody at random in the school, they're going to eat hot lunch that day. Draw a histogram of the binomial distribution based on the probability that exactly K students in a class of 8 students eat the school lunch. So what we're going to do is we're going to find the probability that each number of students is eating the hot school. When they say school lunch, they mean hot lunch. And this is going to be over the next 2 slides, and then we're going to make a little bar graph. That's what a histogram is. So we're going to start off with being 0 students. So it's the probability that the number of students eating is 0. So if the probability that no students eat, if normally an average of 28% eat. So we have 8 students in the class. We're going to do a combination, 0 eating. And then the chances that they are eating is 0.28, and then on a normal day, but we're seeing that 0 kids are actually eating that day, and then 0.72. Oh, I'm sorry, I should explain where that comes from. So if I take, I'll do this up here. If I take 100% and subtract 28%, I get 72%. So that's kind of how I'm thinking about this 0.28. I'm thinking of it in terms of percents and subtracting it from 100%. And so this would become 0.72 to the 8th power. And we would type all of that into our calculator, and it comes out about 0.07. So if normally, on average, 28% of the kids eat, the chances on a given day that nobody eats would be about 7%. And then we just have to repeat this for, okay, what if one kid eats? So this is where that thing that I was talking about, where you don't have to type the whole thing in every time, would come in handy. Mm-hmm. So all we're changing now is, instead of 0 eating, I have 1 eating. And instead of 8 not eating, it's 7 not eating. And we would just type it all in again. Or, like I said, you could copy it and put the new numbers in. And that chance is a little bit better. It comes out 0.22, which is 22%. And then you do the same thing if 2 kids eat. Forgot to put my equals in here. And so we change it to 2 kids eating out of 8. 0.28, there's 2 eating. 0.72, 6 not eating. So you just change the numbers a bit, and that chance is a little bit higher. It comes out 0.31. I'm going to go ahead and do another one in this box since I have room. If not, we can go underneath the box if we need to. So
you do it till you get to 8?
You do it till you get to 8. So this box and the next box we're going to fill in. Good question. Yes, we're going to do it all the way up to all 8 kids eating, and then we're going to make a little graph. So if there's 8 kids, we're now doing the probability that 3 of them eat. So we're going to change our numbers. So it's 28% that on a normal given day, or 28% of the kids will eat hot lunch. We're going to say this day 3 of them are eating. And then the 72%, the 0.72 the chances that they wouldn't eat. And then there'll be 5 kids not eating, and that comes out about 0.24. So it's coming back down. So like the highest chance would be, for some reason, that 2 kids are eating.
Yeah.
And then we're going to go over into the next box. I just made 2 boxes for this because I knew it was going to take a while. So then we'll do the probability that 4 kids eat. So you have 8, see 4, 0.28 to the 4th, 0.72 to the 4th. And that comes out about 0.12. Just kind of hustle through these. 5 kids, you have 8 kids. We're looking for 5 of them eating. Just making sure this all adds up to 8. I'm not making mistakes. That comes out 0.04. So not a very good chance. Go on to k equals 6. So 6 kids eating. Since normally only 28% eat, that's why these are getting to be lower, because normally not very many kids eat. So the chances of a whole bunch of them eating would not be very high. So we do 6 on the power, and then 2 on the power. And this one comes out 0.007. We're almost done. We've got to do 2 more. So then if we do 7, get 8, C, 7, 0.28 to the 7th, 0.72 to the 1st, comes up 0.0008. I'm going to have to go below the box. And then we do the probability of all 8 kids eating. Since normally, on a normal day, it's 28% on average, this is not going to be very high. So we'll put in 8 for that power, 0 for this power, and this one comes out 0.0004. All right, so all of this information is going to go into a histogram. So we did this on purpose, and theoretically, this is going to be a histogram, so which is just a special kind of bar graph. So histogram of binomial distribution. Here's our graph, and I was nice. I set this up for us. And so they've got the probability over here divided into tenths. So basically 10%, 20%, 30%, all the way up to 100%. But they did decimals since that's what we have. So the probability of 0 kids eating was 0.07. So that's going to be just a little bit below 1. So I'm going to fill in a little box that's just a little bit lower than 0.1 because that was 0.07. And then for 1 kid eating was 0.22, so that goes a little bit above the 0.2. Let me color this in. And then we had the probability for 2 kids eating was 0.31, so just barely above the 0.3. Kind of stair steps there. And then it comes back down when we did 3 kids. It comes down to 0.24. Just a little bit less than halfway between 0.2 and 0.3. And then for 4 kids, it was 0.12, so just a little bit above 0.1. It's coming back down. And then for 5 kids, it's 0.04, so that's less than half of a box right there. And it's going to get hard to graph anything. So the 7 and the 8, so let's see, 6 is 0.07, so you could kind of just put a little sliver there. And then 7 and 8, we can just kind of put a little line on the 0 because they're practically 0. Mm-hmm. Okay, so this is what we would call a skewed distribution. So this is technically skewed to the right, which means that it kind of has this rounded part on the left and then it sort of has this tail off to the right. It is not symmetric. And basically the reason why it's skewed, if you remember in the original problem, on a normal day, the average eating the hot lunch was 0.28. And so 0.28 is here, and so it's going to be, if you think about 8 kids, that's around a quarter of them, and it's just going to be over here. So the last slide just shows you what it would be like if it actually came out symmetric. You'd have this nice bell curve. And that's just to sort of show you what a symmetric one would look like. Now, I want to do a little bit more on the other page. I should have had you guys glue this on the left page and go to the right, but it's fine. So if we go back to the left-hand page, which I didn't put a title on yet, we'll just ignore that. I'll do that later. I want to talk a little bit about if they ask us for just pieces. So let's say that we're going to roll a die. So we're rolling a die, which is 1 dice. Okay? And so let's say that we want to find out the probability that we are... I'm trying to think how I want to word this. No, I'm changing my mind. Let's erase that. That's why we're working in pencil. We're not rolling a die. Yeah. Let's talk about multiple choice test. So let's say I'm just going to call it an MC, multiple choice test. And let's say that there are, I don't know, 6 questions on the test. And you didn't study, you have no idea, you slept through class. You're going to have to guess on every question, and for each question, there are 3 choices, A, B, or C. Okay, and all you want to do is get more than half. So let's say that we want to find the probability of getting at least 4 correct out of the 6 questions. Sorry, there's a little bit of stuff from our picture in yesterday's lesson bleeding through there. So we want to find the probability of getting at least 4 correct out of 6. Mm-hmm. So basically, if we think about that, you want to talk about getting 4 correct, 5 correct, or 6 correct. And so we would have to figure out the probability for each of those and then add them up. So
we would go like...
Right, so you're not going to start with 0, 1, 2, 3. You're just going to do 4, 5, and 6 because you want at least 4. Yes. So we're going to set this up. So there are 4 questions. We're going to find a combination. For this one, since we're getting 4 correct, or actually, I'm sorry, there's 6 questions. There's 6 questions. We're trying to get 4 correct, so 6C4. Then we have to figure out what is the probability of getting the problem correct if there's 3 choices. So that would be 1 chance out of 3. Mm-hmm. And then we are going to get 4 correct, so the power is 4. So if there's 1/3 chance you're going to get it correct, you subtract from 1, so 1 minus 1/3 is 2/3. That means there's 2/3 chances we're not going to get it correct, and so that would be 4 correct and 2 incorrect, and we could type those in. So I'm going to do that really quick. So math, go to probability, number 3. All right, so I'm going to put my calculator up here. So let me do that again. I hit the math key, go over to probability. I'm choosing number 3, and then I'm going to put in my numbers 6 and 4. And then I'm going to do 1/3 in parentheses to the 4th power, and then 1/3 in parentheses to the 2nd power, and, oh, I'm sorry, 2/3. I made a mistake. I think I got it all right, and then I can hit enter. So the chances of getting 4 correct out of 6 is about 8%. So I'm going to write that down as 0.0. I'll keep a couple decimal places. This is a little bit bigger than 8%, so it's about 8.2%, so 0.082. And then when I go to set up the second one, I'm going to change the 4s to 5. So I'm going to have 6C5, 1/3 to the 5th power, 2/3 to the 1st power, because now I want to get 5 right, 1 wrong. And so this is where not typing everything back into the calculator would be nice. So if I just up arrow to where I typed this in before and hit the enter key, it'll put everything in there and I can just change the numbers. So I put a 1 here. You just want to make sure you type the first one in right, because if you didn't, you'll miss all of them if you do this. Okay, so I changed the 4s to 5s and the 2s to 1s, and I can do enter. So I'm getting about 0.016 that I can write down. So 0.016. And then we'll do the chances of getting all 6 right, which is not going to be very likely. So I'll change the 5s to 6s and change the 1s to 0s. And I'm just going to leave the formula in the calculator the way that I have it. So I'm going to go up here and just copy this one, change the 1 to 0, change the 5 to 6, change this to 6. So not very likely, it's basically 0%, but we'll say it's 0.001. It's like very unlikely that you would get all of them right if you're guessing. So then the probability of getting all of them, we add it up.
Oh, okay.
So 6, 7, 8, 9, this would be 9, 9. So 0.099 would be your chances of getting all of them right. You could round, or of getting at least 4 out of 6. So you could round this up if you want and say it's about 0.1, which would be about 10% chance of getting 4, 5, or 6 right, which would basically be passing. You have about a 10% chance of passing the test if you didn't study at all and knew nothing about the questions. Normally, we don't go in and completely guess and just circle random stuff, but if you did, that would be your chances.